So we have organic chemistry defined as the special part of chemistry that deals with compounds containing carbon. Even though the majority of the compounds containing carbon are composed of just a few different elements like carbon with hydrogen mostly, and then we have some oxygen atoms there, nitrogen, sulfurs, and phosphorus. Even though it's just a few different elements, we have a large number of organic compounds, and that's due to the fact of how carbon can form different types of chemical bonds, all of them covalent, but we can have single, double, or triple bonds or any or some other different structures. Like in here, for example, you have um, compounds containing only single bonds, like the first one here. You have one carbon bonded to hydrogen only, four single bonds around carbon. You have compounds where carbon starts forming bonds between carbon atoms. So not just something like two carbon atoms bonded together, but you can have many carbon atoms forming bonded together. Like in that specific compound there, one of these hydrogens here can be replaced by another carbon, and the chain of carbon can keep increasing. You can have organic compounds containing double bonds like ethene right here at the bottom, and triple bonds. You can have a combination of single bonds with double bonds, single bonds with triple bonds. You can have a long chain of carbon bonded together with single bonds, and then just one double bond in one between two carbons in your long chain of carbons. And also carbon can form rings or closed compounds like that one right there, which is something that we're going to go over later. So this is a general representation of the different compounds, ways of representing them. We all know the molecular formula. We use that a lot. So when we have a molecular formula, that one is just showing you the types of atoms that you have in a compound, and you will have subscripts telling you how many for each type of atom, if of each type of atom in the compound. So I'm going to give you one example. So a molecular formula will look like this one here, where you have just carbon and hydrogen for this specific compound, 6 carbons, 14 hydrogens. That molecular formula that I'm writing represents the same that you have right here. The representation that we have right here, it's a representation using an expanded formula. When you have an expanded formula, what you have, it's a Lewis structure. You're showing how everything is connected, and you're showing all of your chemical bonds. Okay, so you have a long chain of carbon connected to carbon, 1, 2, 3, 4, 5, 6 carbons, which is the same amount that I wrote here in that molecular formula. Now remember, carbon can form only 4 bonds. You will never have a compound with a carbon with more than 4 things around it. Okay? 4 bonds. A maximum number of electrons of 8. 8 electrons, because carbon is in period 2 in the periodic table. Elements in period 2 cannot have expanded octets. The largest number of electrons that you can have for any element in period 2, it's 8. So for carbon, you have to remember just 4 bonds. So you have your chain of carbons all bonded together in your expanded formula. And you can check your hydrogens. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 hydrogens. So you have C6H14. So another example for molecular formula C5H12. So I'm going to write down my expanded formula using my molecular. You have 5 carbons, so I'm going to write down 1, 2, 3, 4, 5 carbons. Everything is bonded together. So I'm going to bond my carbons with a single line. Now I'm going to write down my hydrogens. I have 12 of them. For each carbon, you can have a maximum number of 4 bonds. The first carbon here, it's connected to the second one with 1 bond, which means that for that carbon to have an octet, you need to have 4 bonds around. Each line represents 2 electrons. So I'm going to put my 1, 2, 3 lines. 2 electrons in each line, which means that around that green carbon that you have right there, you have 8 electrons. For each line, you need a hydrogen. You see, C5H12. So I'm using my hydrogens. I need to use all 12 of them. The second carbon, right here. You see, for that carbon, we already have 2 bonds, right? Connecting that blue carbon with the green one and the next one. So you already have 4 electrons around that carbon, 2 in each line. So to complete your 8, you need 2 more hydrogens. The next carbon here is exactly the same. The next one is exactly the same. This one right here, you already have 2 and 2 electrons right there, which means that that one to go to 8 electrons needs 2 more and another 2. And then the carbon at the very end right here, that one is connected with just 1 line. See, just that one. So you have 2 electrons in that line. And to go to 8, from 2 to 8, you're missing 6 electrons. 6 electrons is the same as 3 lines, 2 electrons in each line. So now you can see that you're using 2, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. So you have the expanded formula for your corresponding to your molecular formula C5H12. The condensed formula, it's a very useful one. It's this one here. It's very easy for you to see the condensed formula and complete like any other of the formulas that you are going to learn about today. So the condensed formula is actually grouping the elements. So when you saw the expanded formula for this one, right? We did that one in the previous page. So for C5H12, if you want to write down the condensed formula, you can have the expanded one. I have my 5 carbons, right? In a similar way to what we did in the previous one, but in the previous one, we were showing all the chemical bonds. Now in this one, you see, You have your 5 carbons. If you check the expanded formula for this one, the carbons on the corners, the beginning and at the end, they have 3 hydrogens. All the carbons in the middle, they have 2 hydrogens. So I'm going to do something like this. This will be CH3 because that's a corner. This will be CH3 because that's a corner. Now, all of the carbons in the middle, they will have just 2 hydrogens each. Sometimes you will get to see the lines. Sometimes you don't get to see the lines. But this formula here, it's a condensed formula. It can be written like this. Or we can have also something that is like a simplification, but you still get to see what it's bonded to what. Since all 3 of these ones are the same, you might see this represented like that. So you have a CH3 at the beginning, a CH3 at the end, and everything that is between your carbons at the beginning and the end will be a CH2. So this formula here is actually telling you the first carbon you have 3 hydrogens bonded to it. In the second carbon you have 2 hydrogens bonded to it. In the third one 2 hydrogens. In the fourth one 2 hydrogens, and then in the last one 3 hydrogens. Now the last type of formula that we have is the skeletal one. This one is the one that gives you the least amount of information that you can actually see. You have exactly the same information, but it's represented in a much more simplified way. When you have a skeletal formula, you don't get to see the carbon symbols or the hydrogen symbols. If you have any element different from carbon or hydrogen, you will get to see the symbol for those elements. But if it's only carbon and hydrogen, you don't get to actually see the symbol. So remember that for carbon, you can have 4 bonds, right? That's what you need. You need 4 bonds around carbon because carbon will form compounds to get an octet. Okay? So carbon will be sharing electrons with other elements, with hydrogen, with other carbons to have a complete octet around. So a complete octet or 8 electrons is 4 chemical bonds. In each bond you have 2 electrons. So now the first line that you have right here, it's giving you the information that you need to interpret that skeletal formula that you have. Each angle, the beginning and the end in your formula represents a carbon. So I'm going to put dots where you have a carbon. You see your formula. Each angle, this is an angle right there. This is an angle right here. This is another angle. And this one right here, it's another angle. So every angle represents a carbon, the beginning at the end, and the end. So you have another carbon here and another one here. So now you can check how many carbons you have in that skeletal formula just by counting. I have 1, 2, 3, 4, 5, and 6. So I'm going to write down C6. Now the lines are representing the chemical bonds between your carbon atoms. So I'm going to do the line in blue. So my first carbon in the corner it's connected to the second one by a single bond. You have just a line right there. That's a single bond connecting those two carbons. If you have one line connecting those two carbons, it means that that first carbon right there in the corner needs 3 chemical bonds to complete the octet. You have only one bond between your two carbons. So one bond is 2 electrons. To get to 8 or the octet, you need 3 more bonds, which means that even though they are not written down, right, you don't have them as part of the formula, that carbon right there, it's actually a CH3. You need to have 3 hydrogens bonded to that carbon for that carbon to have a complete octet. Now, moving to the second carbon, I'm looking now at this one right here. In that second carbon, I'm going to put numbers. In that carbon number 2, that carbon number 2 is bonded to carbon 1 and to carbon 3. Sorry. Let's put number to all of them. So you have that second carbon is forming a bond with carbon 1 and also with carbon 3. So for that carbon number 2, you already have 2 chemical bonds to 2 other carbons, which means that if you already have 2 chemical bonds in that carbon, what you're missing to complete the octet is 2 more bonds. Those 2 bonds, it means that you have 2 hydrogens bonded to that carbon, carbon number 2. Now looking at carbon number 3, something similar to what you have for carbon number 2. Carbon number 3 is bonded to carbon 2 and carbon 4. So you already have 2 bonds around that carbon 3, which means that to complete the octet, that carbon 3 needs 2 hydrogens. So that will be another CH2. And that's your carbon number 3 right there. Carbon 4, same as carbon 2 and carbon 3. Carbon 4 is bonded to carbon 3 and carbon 5. So you already have 2 chemical bonds for that carbon 4. And if you already have 2 chemical bonds for carbon 4, what that carbon is missing to complete the octet is 2 more bonds. Those 2 bonds are 2 hydrogen. So that's your number 4. Carbon 5, exactly the same thing. Carbon 5 is bonded to carbon 4 and carbon 6. So you already have 2 bonds to that carbon 5, which means that for that carbon 5 to have an octet, it needs 2 more bonds. So that will be another CH2. You see, your carbon number 2 here is bonded to carbon 1 and carbon 3. So you already have your 2 bonds and you're missing 2 hydrogens. Same thing will happen with number 3, 4, and 5. Now for carbon number 6, what you have is just one chemical bond. Carbon number 6, it's bonded to carbon number 5, nothing else. From your formula, you don't have any other chemical bonds. So for that carbon 6 to have a complete octet around, since you have only one chemical bond right there, you need 3 more. Okay? So to get to 8, if you have 2, you need 6 more. So that's 3 more chemical bonds. In each one you have 2 electrons. So that carbon number 6, it's a CH3. So now I'm going to write down here C5H12, and you need to write down the skeletal formula for C5H12. So I'm going to give you a couple of examples of skeletal formulas for you to transform to the expanded formula. So you should be able to do in like the same thing, but in the opposite direction. If I give you the expanded, you should be able to transform that into the skeletal formula. So that will be the first one. Second one. Third. And a last one. Now, a couple of things. I'm going to do one of them, and then you can complete the other ones. I'm going to do the second one. When you have your skeletal formulas, if your compound is entirely made of carbon and hydrogens, you don't get to see any symbols. In your skeletal formulas, the symbols that are omitted are for carbon and hydrogen. If you have an atom different from carbon and hydrogen, like oxygens or nitrogens or sulfurs or phosphorus, that symbol will actually show. If you have the symbol, wherever you have a symbol, you don't have a carbon. You have carbons at the beginning, at the end, in each angle, as long as you don't have the symbol for any other element. So what that means is that for that second structure that you have, I have carbons at the beginning, at the end, in every angle. I have one angle right here, and I have a second angle right here, but you have an oxygen symbol there, which means that you don't have a carbon right there. What you have is an oxygen atom. So I'm going to start by writing my two carbons here. That's my expanded for that one. I have a carbon in the corner. I have a carbon right after that one. The third thing that I have is an oxygen, and then I have another carbon. Okay. So now I can write down my lines between the first carbon. Let me put numbers 1 and 2. The first carbon and the second carbon, you have one line, just one. So I'm going to draw a line right there. Between the second carbon and the oxygen atom, you have another line. So I'm going to put my line right there. Between the oxygen and carbon number 3, you have another single line. So I'm going to put that line right there. So now what you need to complete is how many hydrogens you're missing. Okay? And we're completing hydrogens only for the carbon atoms. Okay? You don't have to complete hydrogens in anything else. If you have a hydrogen bonded to an oxygen, the hydrogen will be showing. Okay? If you have something like OH, the hydrogen will be right there bonded to your oxygen in the skeletal formula too. So actually, let me add that here so you get to see it. So now I'm going to complete my hydrogens in the second formula that I have right there. The first carbon is bonded to the second carbon with a single line. That's 2 electrons. So for you to complete the octet to that carbon, you need 4 bonds. So you already have 1 bond connecting your 2 carbons. So to complete 4, you need 3 more. So that means that you have 3 hydrogens bonded to that first carbon. The second carbon, carbon number 2, you have 2 bonds in that one. You have one bond that goes to the oxygen and you have another bond that goes to the first carbon. So if you already have two bonds, you're missing two more bonds to complete the octet or to go to 4 bonds. So I'm going to put 2 more bonds for the hydrogens. The oxygen, we're going to keep that one as it is. In your formula, in your skeletal formula, you don't get to see any bonds to that oxygen besides the 2 that you have for the carbons. So I'm going to move to the last carbon right there. The last carbon is bonded to the oxygen and nothing else. So you have only one chemical bond in that last carbon. So you need to complete 4 bonds. So if you already have one, you're missing 3 more bonds to get to 4 bonds around that carbon in the corner. So that will be the expanded formula that corresponds to that skeletal formula right there. For the first example, I'm not going to work it for you. Remember, you have a carbon in the beginning, at the end, and each angle. What is different in that first one is that between the the second carbon and the third carbon, I'm starting counting on the left side. Between the second and the third carbon, you don't have just one line. You have 2 lines between those 2 carbons. What that means is that between those 2 carbons, you don't have a single bond. You have a double bond. And the double bond means that you have one less hydrogen because you already have 2 bonds to those 2 carbons, the second one and the third one. For skeletal formula number 3, the third one that you have listed there, you see how you have right here, this is an angle, okay? That's an angle. You don't have the symbol for an element in there, which means that that angle right there represents a carbon. That carbon has a double bond to the oxygen atom that it's showing right there. The last one is the one that I added the hydrogen to the oxygen. You see, in that oxygen atom that you have right there, you have a hydrogen bonded to it. If you have hydrogens bonded to any atom different from carbon, the hydrogens are going to be showing up. The ones that are not showing up are the ones that are bonded to the carbon, because you can actually determine how many hydrogens are bonded to the carbons based on the rule that carbon forms 4 bonds. So you can look at how many bonds you have for each carbon, and you can just complete how many hydrogens you're missing to complete the 4 bonds for each carbon. When you have elements different from carbon, then your hydrogens, if you have them, they will be showing up. Now here we have a list of organic compounds classified by functional groups. So some of them I'm going to go over very quickly, and then at the end I will give you a summary. What you need to know is how to recognize these functional groups in your compounds. The functional groups, what a functional group is, or the functional groups, what it is an atom that is replacing a hydrogen atom in an organic compound, or a group of atoms, not just one, that is replacing a hydrogen atom in organic compounds. Now, it's classified as a functional group because you will have different compounds containing that same atom or that same group of atoms. Not exactly the same formula, but they share that functional group. They have that in common. When a group of organic compounds share the same functional group, they will have similar properties, similar reactivity. usually they react to give you a specific type of compound. So you have a list here, and I'm going to go over them individually. Starting with the hydrocarbons. Hydrocarbons are your organic compounds that are composed entirely of carbon and hydrogen. That's why they are hydrocarbons. So there's nothing else there. Only carbon and hydrogens. You can have single, double, or triple bonds, a combination of them, but only hydrogen and carbon. You should find the definition of aliphatic. So for your hydrocarbons, I'm going over them like individually, but you have alkanes, alkenes, and alkynes, and also aromatic hydrocarbons. In general, your hydrocarbons, the boiling points if they're liquids, the melting points if they're solids, they are usually low. And as the size of your compound increases, so does the boiling points or the melting points. You have right here this table. First column is telling you number of carbons. So when you have hydrocarbons with a number of carbons between 1 and 4, they're usually gas. They're usually at room temperature, they are gases. Now, when the number of carbons starts increasing, you see 5 through 7. Now, the physical state is different. You have now liquids. The larger they are, the more intermolecular forces you will have. And now it's possible for you to have those type of compounds in a liquid state at room temperature. They're liquids, but they have low boiling points, which means that at a slightly increase in temperature will evaporate those liquids. And then we move to hydrocarbons containing 6 carbons to 18 carbons, and they are at room temperature, they will be liquids. And you can see the other ones. Now, saturated hydrocarbons and unsaturated hydrocarbons. Remember, you have your hydrocarbons, it's just compounds containing carbon and hydrogen and nothing else. So saturated hydrocarbons, what that means is that you have only single bonds. If you have only single bonds, they are known as saturated because each carbon will have the maximum number of hydrogens that they can possibly have to complete the total number of bonds equals to 4. That's why they are saturated. They're saturated with hydrogens. So those saturated hydrocarbons are alkanes. ANE is the ending of the name. And alkanes are hydrocarbons containing only single bonds. Since they have only single bonds, your carbons will be saturated with the maximum number of hydrogens that they can have. Now for unsaturated hydrocarbons, we have 2 different types. We have alkenes, ENE, and alkynes, YNE. Alkenes and alkynes, they are unsaturated because they have double or triple bonds, which means that the number of hydrogens in each compound will be decreasing. They are not saturated with hydrogens because now you have multiple bonds between the carbons. When the number of bonds between carbons starts increasing, the number of hydrogens starts decreasing. You need less hydrogens to complete the 4 bonds around the carbons. So alkenes, ENE, those are your hydrocarbons that contain at least one double bond. Alkynes with Y and E, those are the hydrocarbons that will have at least one triple bond. Another thing that you need to know from this part here, let's put my alkanes in green and that formula right there. I'll go over that. E and E, double bonds, alkenes, and that formula right there. Alkynes, Y and E, triple bonds, with that formula right there. What the formula represents, look, starting with alkanes, Cn, that N, it's a numerical value. It's telling you how many carbons you have. If you know how many carbons you have, and you know that it's an alkane, single bonds, you can calculate how many hydrogens you will have in total depending on the number of carbons that you have. And I will give you an example for each one. But that N is telling you how many carbons. Say 5. If you have 5 carbons for an alkane, how many hydrogens are you going to have for 5 carbons? If N is 5, you can calculate the number of hydrogens. 2 times N plus 2. So if N is 5, your number of hydrogens is going to be 2 times 5 plus 2, which is 12. That's what the formula is telling you. The formula is useful for you to calculate how many hydrogens you have depending on the number of carbons. So you need to know how many carbons in order for you to be able to calculate how many hydrogens you have. The same thing applies to your alkenes and alkynes. You see, for your alkenes, if you have 5 carbons, C5, that N value is 5, then you can calculate your number of hydrogen. If it's alkene with 5 carbons, your number of hydrogens will be given by 2 times 5, which is going to be 10. For alkynes, your formula is Cn. N is how many carbons you have. So if you have 5 carbons for an alkyne containing at least one triple bond, let's assume that is just one triple bond, you have C5. So now the number of hydrogens is going to be given by 2 times 5, which is 10, minus 2. So when you have an alkene with 5 carbons, the number of hydrogens that you will get is equal to 8. So let's do that. So let's calculate the number of hydrogens if you have, we did 5, let's do 7 carbons. If I tell you, okay, you have an alkane with 7 carbons, how many hydrogens do you have for that alkane? So you have 7 carbons, that's the value of N. The number of hydrogens will be 2 times 7 plus 2. That's 16. So the formula for your alkane, all single bonds, will be C7H16. Now, if what you have is an alkene with one double bond, you're not going to have 16 hydrogens because alkenes are unsaturated. The maximum number of hydrogens that you can have when you have 7 carbons, it's 16. So that's a saturated hydrocarbon because that's the maximum number of hydrogens that you can get. When you have a double bond, now the number of hydrogens is going to be lower. So we can calculate, still see, I'm doing the same for the same number of carbons, 7 of them. C7. Now to calculate the number of hydrogens, your formula is telling you that it's going to be 2 times 7. So that will give you C7H14. The last example for an alkyne, the formula is Cn H2n minus 2. So if n is equal to 7, if you have 7 carbons, the number of hydrogens will be given by 2 times 7 minus 2. So you see how the number of hydrogens it's decreasing. As the number of bonds between carbons starts increasing, the number of hydrogens is decreasing. So the first one is desaturated, only single bonds, and then your alkenes and alkynes, they are unsaturated. Now you have aliphatic hydrocarbons, which means that you need to find that definition. And for those, we have alkanes, alkenes, and alkynes. Saturated with hydrogen, your alkanes, only single bonds. Unsaturated, your alkenes, and your alkynes with double and triple bond respectively. So aromatic hydrocarbons are those compounds containing a special structure, which is known as benzene. Benzene is just a cyclic hydrocarbon, which means that you have a ring containing 6 carbons and alternating double bonds between the carbons. So I'm going to make the drawing because you're going to see a lot of benzenes in your organic chemistry. So the structure for benzene, it's a cyclic compound containing 6 carbons. Each angle represents a carbon. Now we don't have a beginning or an end because it's a cyclic compound. When you have compounds in a chain, you will have a starting point and an ending point. When it's a cyclic compound, you don't have a beginning and an ending. So here, all of your carbons are given by angles. So you have 6 carbons in that structure. But what makes benzene aromatic compound or aromatic hydrocarbon, it's the double bonds. Alternating double bonds, which means that you have a double bond followed by a single bond followed by another double bond followed by a single bond. So I have my first double bond right there, single double bond. That's exactly the same as, I'm still going to put your red dots for the carbons. They're exactly the same. If you start with your double bond right here, alternating double bonds, the next one will be single double. They represent the same thing. It's just that the double bonds are in different between different carbons, but they're the same. Another way of representing those structures, it's like this, with a circle. All of them represent the same thing. Whatever you see a formula like that, that represents an aromatic compound. Sometimes you have substitutions in the formulas like this. So in that carbon right here, you have an oxygen bonded to a hydrogen atom. But it's still an aromatic compound because it contains that benzene structure. So for benzene, you just need to recognize, like if you have that benzene ring, that's benzene, an aromatic compound. A little bit more about your hydrocarbons. In this table here, I'm showing you different hydrocarbons, but the important part, it's what the name is, the information that the name is giving you. You see, the first one that you have right there, N1, means that you have just one carbon. The name for that hydrocarbon containing one carbon is methane. That name has two parts. One part that I'm going to put underlining green. The second part that I'm going to underline in red. The first part in the name is telling you how many carbons you have in that compound. Methane, that name corresponds to an alkane with one carbon. Alkane because that second part is telling you the specific type of hydrocarbon that you have. So meth, the beginning, underlining green, that part of the name tells you how many carbons you have. The ending of the name is telling you which specific type of hydrocarbon you have. A and E is the ending of the name for a compound that is an alkane. Second one, ethane. The beginning of the name is telling you that that's a compound that has two carbons. Whenever you see something with that beginning of a name, prop, means that you have three carbons. Bute is what we use for four carbons. Pent is what we use for five carbons. In green, hex 6. I will tell you what that N represents later. Hept for 7, 8, 9, and 10. So with the name, you can find out two things. You can find out how many carbons you have for that specific compound. You can find out which specific type of compound you have. A and E is telling you that that compound is an alkane. The beginning of the name will tell you how many carbons you have. This is the same table, but now with double bonds. If you look at the beginning of the name, we don't have the first one here, methane, because for you to have a double bond, you need to have at least two carbons to place that double bond. It's double bond between carbon atoms. So for methane, you have only one carbon, which means that you will never have an alkene with just one carbon. The simplest alkene that you can get is with two carbons. So the beginning of the name, you can compare these ones with the previous table. Look, two carbons, ethene. Now the ending of the name is different because what you have is an alkene. The beginning is the same. 4, 5, 6, 3 for prop. The ending is ene because now we're looking at alkenes. Now you see how I erased some n's in the names for the previous table. What that n is representing is a number. It's a number where you have the double bond. So you see how you have here butene, one butene. One butene means that butene, ene, you have an alkene. Alkenes, they have double bonds, right? So if you have one double bond, it will be in the first carbon. That's why you have one butene. So you know that number is telling you just where the double bond is. But you don't have to worry about that. What I want you to know is how many carbons you have depending on the name, and which specific type of compound you have depending on the ending of the name. ANE is for alkanes, ENE is for alkenes, and then you can guess that the third type of hydrocarbon is alkynes with YNE. So if the ending of the name is YNE, what you have is an alkyne. YNE, you see the name for all of them ends in YNE because they are alkynes with triple bonds. You can see the formulas there. The beginning of the name is the same for all because that beginning of the name is just telling you how many carbons you have for each one. Same thing as with the alkenes. You don't have one with just one carbon bond. Methane is the simplest organic compound that we can have with just one carbon. So you cannot have methane or methane because you need at least two carbons to have a double or a triple bond. So the simplest alkyne that you can have will have two carbons, same as the alkenes, at least two carbons for you to have the double bond. So this is just a summary. Okay? The beginning, which is here parent, is telling you the length, or how many carbons. The ending, which is this part here, the suffix, is telling you which specific type. A and E for alkane. I'm missing an E right here. That will be alkene. And then Y and E for your alkynes. So that's like kind of a summary. The beginning of your name telling you how many carbons you have. Ethane, propane, butane, pentane, hexane, heptane, octane, And then you have for 9 and 10, at least for the first 10, make sure that you have them in a piece of paper. And then the second part of the name is telling you which specific type of hydrocarbon you have, saturated or unsaturated. Now we're going over specific functional groups. So we have the hydrocarbons, only carbon and hydrogen, nothing else. Now for this part, we're actually going to see other atoms besides carbon and hydrogen, and those atoms are going to be part of a specific functional group. So I'm going to show them to you very quickly, and then I will give you a summary and what you have to focus on. The first functional group that we're looking at is alcohols. Alcohols are organic compounds containing the hydroxyl group. Hydroxyl is this part right here. It's OH, an oxygen bonded to hydrogen. This R that I have right here, that's any part containing carbon. You can have one carbon, two carbons, 20 carbons, okay, with the respective amount of hydrogens. It's a generic term that we use because you can have any R, any number of carbons, hydrogens there, but as long as you have that hydroxyl bonded to that R, you will have an alcohol. So we can look at these three examples that I have right here for you to see what that R represents. You see, the first one is ethanol. Remember, that is not changing. You see how you have that the beginning of your name, eth, is the same that you have for ethane, ethene, and ethine. That beginning of the name means two carbons, regardless of which compound you have. If that's the beginning of your name, that's always for two carbons. That's one thing. Now, the R is exactly that part. You see, you have right here CH3, CH2. And then you have the OH, which is what makes that compound an alcohol, that hydroxyl group. The blue part that I'm underlining is this R. So that's just the generic part. You can have any part right there containing carbon, and as long as you have the hydroxyl, you will have an alcohol. Let's check this second one. You see you have your hydroxyl right here. So that means that you have an alcohol. The last one right there. Right there. And also you can underline this in blue. Those are your R's. You see you have different R's. You have CH3, CH2. You have two CH3s here. You have a CH right there. All of that represents that R. And you have your hydroxyl group, so that's an alcohol. And then the last one here, you have your R right here is just CH3, and then you have your OH, so that's an alcohol. So another thing besides looking at the name and knowing how many carbons you have, that does not apply to isopropyl, even though you can actually see because you have prop right here, and prop is what we use for 3 carbons. Smet is what we use for 1 carbon. So besides knowing how many carbons you can have depending on the name, you can also identify specifically which type of compound you have. Well, this name is telling you When you have alcohols, look right here. The name ends in OL, like alcohol. So if you have that, just the name, I'm not giving you a formula, just the name, hexanol. If you go back to the table with the names, that's what we use for 6 carbons. So just by looking at the name, you can tell that that compound it's going to have 6 carbons. Now, that part of the name is telling you that that compound contains an hydroxyl group, which means that that's an alcohol. Hexanol, butanol, propanol, ethanol, heptanol, octanol, all of them are alcohols because the ending of the name is OL. So if I give you a list of names and I ask you which one is an alcohol, you should be able to identify it because of the ending of the name. If I give you a list of compounds and I ask you which one is the alcohol containing 4 carbons, you should be able to find that because the name is telling you how many carbons in the beginning of the name, and the ending of the name is telling you if you have an alcohol or not. Now I have two compounds, two functional groups here, aldehydes and ketones. So both of them, what they have in common is a carbonyl group. Now a carbonyl group is this, that right there. It's a carbon, double bond, oxygen. So you can actually see that you have carbonyl in all of my structures right here. I have a carbonyl here, I have a carbonyl here, here, and here. The carbonyl group is not the functional group. You have a functional group for aldehydes, you have a functional group for ketones. Both of them are going to contain carbonyl, but the carbonyl is going to be bonded to different things if you have an aldehyde or if you have a ketone. If you have an aldehyde, the carbonyl is bonded to hydrogen. If you have a ketone, what you're going to have is carbons bonded to that carbonyl. So let's check my structures. The first one that you have right there, you have your carbonyl here in blue, right here. And you can see that that carbonyl, it's bonded to a hydrogen atom. The second one, the carbonyl, it's bonded to a hydrogen atom. Now for the third one and the fourth one, you see your carbonyl right here. You don't have a hydrogen bonded to that carbonyl. Look, you see how this is a CH3. These 3 hydrogens here, they're not bonded to the carbon that you have, the carbonyl. These three hydrogens here are bonded to that first carbon like this. So your carbonyl in this structure here is bonded to a carbon right here and another carbon right there. So you can see that the carbonyl is bonded to carbons, and you have that when your functional group is a ketone. The last one, same thing here. Look, this CH2, those two hydrogens are bonded to that carbon here and here. So your carbonyl is bonded to carbon atoms right there. And that's a ketone. So I have aldehyde, and for that one too. Carbonyl bonded to hydrogen, your functional group is an aldehyde. Carbonyl bonded to carbons, that's ketones. So what you need to know is you have to be able to identify which functional group you have. If I give you a list of structures and I ask you, okay, select which one corresponds to the functional group of a ketone, if it's a ketone, you know that you need to have a carbonyl. We didn't have a carbonyl for alcohols, but for ketones and for aldehydes, you do have a carbonyl. So you can start by looking only at the ones that you have a carbonyl. Then, if you need a ketone, that carbonyl has to be bonded to carbon atoms. If you need an aldehyde, your carbonyl has to be bonded to hydrogen. Okay? Another thing, if I give you the name, just the name, not a formula, based on the name, look, ethanol, again, 2 carbons, propanol, 3 carbons, prop, 3 carbons, and this one was bute, which is 4 carbons. Just with the name, you can know how many carbons you have. Another thing that you can determine is, look, aldehydes, the name ends in al, like aldehydes. If it's ketone, the name ends in o and e, o, like ketone. That's the name. So when you have propanone right here, you know that you will have 3 carbons because that's for prop, and o and e means that you have a ketone. These are just some other examples. So you have ONE ketone, ONE ketone, ONE ketone. So these ones are ketones with aromatic parts, and they have odors, and some of them also have flavors. Another functional group is carboxylic acids. So this is a way of representing a carboxylic acid, and you already know some things about carboxylic acids because carboxylic acids are weak acids. So whenever we talk about acetic acid is a weak acid, and actually what you have for acetic acid, it's a carboxylic acid. So that's one way of representing that functional group. Another way is this. You have a carbonyl right here for carboxylic acids. You have a carbonyl. Your carbonyl is bonded to the hydroxyl. Now, common mistake is mixing together alcohols and carboxylic acids. The difference between an alcohol and a carboxylic acid is that For alcohols and carboxylic acid, for both of them, you get to see the OH. But for alcohols, you don't have a carbonyl. You do have a carbonyl for carboxylic acids, but not for alcohols. So you can look at this structure here. You see how you have OH, you have OH, you have OH here, you have OH here. Out of all of those OHs that I underline, only one of them corresponds to hydroxyl, what you have for an alcohol, because only one of them is not bonded to carbonyl. You see how you have your carbonyl right here bonded to OH, carbonyl bonded to OH, carbonyl bonded to OH. So all of those carbonyl bonded to OH is the functional group that you have for carboxylic acids. Now this part right here, you don't have that OH bonded to a carbonyl, right? So if your OH is not bonded to a carbonyl, that functional group represents an alcohol because it's not bonded to carbonyl. All of the ones that you have bonded to carbonyl, they represent functional groups for carboxylic acid. Now, identifying carboxylic acid based on the name is too easy because you will always have the word acid. So like acetic acid is a carboxylic acid and you have that as part of the name. So all of your carboxylic acid, the naming will include that acid word. And you don't have any other acids for functional groups, just carboxylic acids. Esters. For esters, you do have a functional group including a carbonyl. COO. It's a way of representing your functional groups for esters right here. And expanded version of that is this one right here. It's still COO. You see, it's the same thing. It's just a different way of representing that specific part of your formula. So when you have esters, you do have a carbonyl, and that carbonyl is bonded to an oxygen atom. You remember we started with compounds containing carbonyl. The first two that we did was aldehydes and ketones. For aldehydes, your carbonyl is bonded to hydrogen. For ketones, your carbonyl is bonded to carbon. For carboxylic acids, carbonyl is bonded to OH. For esters, carbonyl is bonded to oxygen, not OH. If you have OH bonded to carbonyl, that's not an ester, that's a carboxylic acid. If you have carbonyl bonded to only oxygen, after that oxygen, what you're going to have is an R group, something containing carbon. That represents an ester. You can see your functional group right here. You see your carbonyl, and that carbonyl is bonded to an oxygen right there. You don't have an H bonded to that oxygen, so it's not a carboxylic acid. What you have bonded to that oxygen that is bonded to the carbonyl, it's something containing carbon, your R, okay? Simplification. You see on the other side, you also have an R group. So you have the ending of the name for esters. It's OATE. So you can recognize based on the name, if you have just the name, not the formula, and the name of that compound ends with OATE, it means that whatever compound you have is going to be classified as an ester. So you can actually classify your compounds based on the name in a specific type of compound, esters, carboxylic acids, ketones, aldehydes, or you have to be able to recognize which type of functional group you have looking at a structure. Like what you have right here. If you have a structure right here, you should be able to look at the functional group. What you have in your carbonyl bonded to oxygen, that will be the functional group for esters. Ethers, very similar to esters, but you don't have a carbonyl for ethers. No carbonyl. You have an oxygen atom between carbons, but there's no C double bond O. That's the main difference between esters and ethers. When you have esters, you do have the carbonyl. When you have ethers, you don't have a carbonyl. It will be an oxygen atom bonded to carbons. So you can see here, again, CH3, those three hydrogens are bonded to carbon right here, not between oxygen and carbon. Hydrogen is never, it's always a terminal atom. It can form just one bond, so you cannot have these hydrogens between carbon and oxygen. This is a condensed formula telling you CH3, it means that those three hydrogens are bonded to the carbon. So you have that oxygen atom bonded to two carbon atoms, and that will be an ether. Amines are organic compounds containing nitrogen, and we're going to have two different types of organic compounds containing nitrogen. Amines is the first one. So when you have amines, you will be able to identify them very easily by the formulas, because you have nitrogens. So if you have nitrogens, you will have amines. But there's another functional group or another category of organic compounds that contain nitrogen too. And those are the amides. The difference between amines and amides is a carbonyl group. You have a carbonyl group for amides, and what you have bonded to the carbonyl, it's a nitrogen atom. So for amines and amides, what you have in common is the nitrogen. So if you see a nitrogen in a formula, that means that you're going to have an amine or an amide. Now, to determine specifically which one you have, you need to look for carbonyl. If you have a carbonyl with the nitrogen, now what the functional group that you have for that compound, it's an amide. If you have nitrogen but you don't have a carbonyl, then the functional group that you have is an amine. So these two are ones that you can mix together. But remember, with the carbonyl, it's amide, and then without the carbonyl, you have amines. So here I will give you the summary. So let's start by writing functional groups. No carbonyl with carbonyl. Organic compounds with no carbonyl, we're going to have alcohols. Functional group OH, that's one. We're going to have ether. Functional group and oxygen bonded to carbons on each side. And amines containing nitrogen. Now, functional groups with carbonyl. Aldehydes. Carbonyl bonded to hydrogen. Ketones. Carbonyl bonded to carbons. Esters. Carbonyl bonded to oxygen. Carboxylic acids. Carbonyl bonded to OH. And I hope I'm not missing any of them. Amides. Carbonyl bonded to nitrogen. So, common mistakes confusing alcohols with carboxylic acids. You do have the hydroxyl group for both, but you don't have carbonyl for alcohol. Another common mistake, ether, confusing ether with esters. For ether, you don't have the carbonyl. For esters, you do have a carbonyl. Carbonyl bonded to oxygen. Amine and amides, you have carbonyl for amides, you don't have carbonyl for amines. Ketones, you have carbons on both sides of the carbonyl. Aldehydes, what you have bonded to the carbonyl, it's an hydrogen atom. So I'm going to write down like some structures for you to check if you can identify which type of functional group you have in each one. Sometimes you can have more than one in the same structure. Using combining different things like skeletal formulas, condensed formulas, and the functional groups. So try to identify the functional groups that you have for these structures, and then you can check your answer to see how many of them you have correct.